Right, in this video, we're going to look at the physical properties and reactivity issues associated with the functional group phenols, shown here by the exemplified here by the simplest phenol of them all, phenol itself. This is a very short chapter. It's going to be done in one video. One of the reasons, or the main reason it is so short, is because you've already had the chemistry of alcohols and you've already had the chemistry of benzene rings, and this ring system kind of just blends the two of them together for most of its reactions. Okay, so physical properties, we can see here that we have a bond between oxygen and hydrogen, so of course it's a hydrogen bond donor and a hydrogen bond acceptor. The physical properties resemble a 6-carbon alcohol with slightly greater water solubility due to its enhanced acidity, which we're going to talk about in a second. Okay, so its boiling point's a little higher than cyclohexanol, its water solubility is a little higher, and it's much higher than than a straight chain 1-hexanol. Okay, all right, so one of the important physical properties of phenols is that they're acidic compounds. They're intermediate in acidity between carboxylic acids and alcohol. So let's look down here at some compounds that are relevant. Okay, so phenol itself has a pK of just a little bit below 10. It's much more acidic than cyclohexanol, which has a pK of 16, a typical alcohol. However, it's not quite as acidic as acetic acid, a carboxylic acid. The pK there is down around 4. Okay, just like we saw with carboxylic acids, electron withdrawing groups enhance the acidity and electron donating groups decrease the acidity. The effect of electron withdrawing groups is much more dramatic than the effect of electron donating groups. Okay, so we're going to put this acetyl group right here in the para position, and we see the pK goes from 9.95 down to 7.7. Okay, we're going to put the electron withdrawing methoxy here in the same para position, and what you see is the pK rises. It doesn't rise very much, goes from 9.95 to 10.2, but this is a general trend that an electron donating group will decrease the acidity. Okay, chlorine is a weakly electron withdrawing group, and we see only a slight drop in the or a slight increase in the acidity here. It goes from pK 9.9 down to pKa 9.2. All right, so what's the reason for this enhanced acidity? It's the fact that we can write resonance structures for the conjugate base of the phenol, which we show here, and this is called the phenoxide ion. Okay. All right, so when we draw a phenoxide, you can see that there are resonance structures you can draw. All right, so let's just go ahead and draw the arrows here that connect these up. All right, so we can delocalize like that, and this will now put the negative charge right here at the ortho position, and we can write another resonance structure just like we did back in the aromatic chapter that puts the electron density, or the negative charge, down to the para position. Okay, so we delocalize the negative charge into the ortho and para positions. Recognize that when we write these resonance structures, we get rid of aromaticity, and because of that, these aren't really all that great a resonance structures, but they do show that we're distributing the negative charge somewhere then completely at the oxygen atom, which would be the case in just a simple alcohol like cyclohexanol. All right. Okay, so let's do an acidity ranking question. We're going to rank the following compounds in terms of their anticipated relative acidity. In this case, some of them are a little bit close in acidity, but if a question like this appeared on the exam, there'd probably be fewer things to rank, and we would choose examples where there weren't any ties. Here we're going to have some of them that are a little bit close. Okay, So what are our considerations? The phenols have a pK of around 10, so do the ammonium salts derived from alkylamines. Alcohols are less acidic, ketones are a little bit less acidic than alcohols, and carboxylic acids are the most acidic of them all. All right, so when we rank these, we're of course going to put our carboxylic acid here probably as number 1. Okay, we have next the phenols, phenol itself, paranitrophenol. Nitro is an electron withdrawing group. Okay, that's going to enhance the acidity. Methoxy is an electron donating group, and that is going to decrease the acidity. So of the phenols, the nitrophenol is going to be the most acidic, then phenol, then paramethoxyphenol. Okay, but we see when we look at this table or these statements down here, what we're going to see is that it's going to be difficult to rank an ammonium salt and a phenol. Okay, so this is going to be kind of ranked around where phenol is. Okay, and of course we're going to have the alcohol second to last and the ketone as our least acidic compound. And here is the rankings. Okay, the ones that I've shown in magenta, there's a little bit of too close for comfort aspect to these, but we could probably say that this one is definitely going to be more acidic than this one, but as to where the amine ranks, that's a little bit hard. You'd probably have to go in the lab and measure it yourself to really get an accurate value. You can't just make generalizations based on the type of functional group you have right there. Okay, but it's the ammonium salt is very close to the phenol. Okay, let's look at how to make phenols. All right, these are one of the hardest functional groups to make. It's comparatively difficult. Every method that we see, we're going to have something about it that we don't like. It's either going to be too long, or it's going to have conditions that are too harsh, or it's going to be work in very specific systems. All right, here's the industrial synthesis of both phenol and acetone. What you do is you take isopropyl benzene, which has the common name cumene, and if you leave it in the air for a long time, it undergoes something called autooxidation, where it forms this compound with the OO bond here called the hydroperoxide, cumene hydroperoxide. If you treat cumene hydroperoxide with sulfuric acid, it'll convert to phenol and acetone in a very interesting mechanism. Let's go ahead and look at this mechanism because it kind of resembles the mechanisms we've had in the past, the Baeyer-Villiger oxidation and the Pinnacle rearrangement kind of combined together in one reaction. All right, so here's what happens. We're going to protonate the alcohol, okay, and can probably protonate either oxygen, but this is the one that's going to move us in a forward direction. Okay, this gives us the protonated alcohol, and now this is now a leaving group, so water's going to leave. If it just left, you'd have a oxygen with a positive charge and just 6 electrons buzzing around it. That's not a very stable species, so as water leaves, the phenol migrates to oxygen to produce this oxonium cation here. And remember, this is the intermediate from acetal hydrolysis back in the ketone chapter. So this is going to react with the water to make the protonated hemiacetal. We're going to lose the proton to make the hemiacetal, and the hemiacetal is just going to fall apart to give you the alcohol and carbonyl compound that it came from. Okay, if you remember back in the aromatic substitution chapter, we had something called nucleophilic aromatic substitution. And if you have a fluorine or chlorine or bromine or iodine too, I guess, any halogen, fluorine's actually the best. And Ortho or para to that is a really good electron withdrawing group like nitro. What happens is you'll do a nucleophilic substitution reaction. Okay, this proceeds through this carbanion type intermediate. Fluoride leaves, and then you get the phenol. Initially, you're going to actually get the phenoxide because this hydroxide base is more basic than phenol, but you'll eventually work it up with some sort of acid, and this will be the product that you get. Okay, the limitation on this reaction is that you have to have the nitro group or whatever really strong electron withdrawing group appropriately placed on your molecule, so only a few specific substitution patterns can be accessed through this reaction right here. Okay, you can actually take a sulfonic acid and heat it to very high temperature. This is the limitation here, KOH at 350 degrees C. These are what we call very harsh conditions. Not many functional groups would just survive this reaction, but if you conduct this reaction and then you neutralize all the KOH, what you'll find is that you get phenol. This is another example of nucleophilic aromatic substitution. At this very high temperature, you add this hydroxide. I'll just show you the arrows here. Okay, so hydroxide ion adds like so. Okay, to give you the anion. And then the sulfate group leaves as a bisulfite group, and you make phenol. Under these basic conditions, you'll make the phenoxide, and you have to acidify later and produce the phenol. Okay, so this is very limited because of the very harsh conditions. You really can't have any functional groups at all if you want to do that reaction. All right, here's the mildest method right here, but it involves quite a few steps, and we had this in the amine chapter. Okay, so if we want to turn benzene into phenol, we can do it in a 4-step reaction where we nitrate, reduce the nitro to NH2 with 10 NHCl or iron NHCl or various other reductants will do that. We're going to turn the NH2 group into the diazonium salt with sodium nitrite and acid. And then we're going to heat this in the presence of water, and the diazonium salt will convert into the alcohol. Okay, this is a simple and general method, but again, its limitation is that it has quite a few steps, but these steps kind of come as a package, as you might recall in the diazonium chemistry. All right, so this is a reaction, the transformation of benzene into phenol. That's a reaction that really still needs to be invented, a really good reaction that will do that in one step. Okay, let's look at the reactions of phenols. And we're going to classify them in 2 ways, alcohol reactions and aromatic ring reactions. What we're going to find here is that most of the reactions we look at in this chapter we've already had before. We're just going to use the phenol, the alcohol part of the phenol to do alcohol reactions, or we're going to use the benzene ring of the phenol to do aromatic ring reactions. Okay, so we can do we can convert the alcohol into the corresponding ester using either the Fischer esterification shown here at the top, where we take phenol and a carboxylic acid and a sulfuric acid catalyst and heat them together. This will make the ester, or a more milder method that doesn't have these equilibrium problems. Remember that you can also hydrolyze it by just treating it with sulfuric acid water. Okay, so a milder method that doesn't have these equilibrium issues involves taking an acid chloride or an anhydride and treating it with the phenol in the presence of pyridine, and this also gives the ester. And this is the milder method for doing it here from the acid chloride or the anhydride. Okay, Phenols react like alcohols in the Williamson ether synthesis. The only advantage here is that since the pKa here is less than 16, you can use sodium hydroxide. You had to use something stronger than sodium hydroxide to pull the proton off an alcohol. But it's perfectly adequate for pulling the proton off a phenol. Okay, so if we pull the proton off here and then treat it with an alkyl halide, we'll do the Williamson ether synthesis to get the unsymmetrical ether that you see here. Okay, and the second step here is merely just another example of, remember, the SN2 reaction. Okay, all right, so we also have a new reaction we're going to talk about. This is called the Claisen rearrangement. And if we have an allyl group, like you see here, or any sort of allylic group on oxygen, we can heat the compound to 150 to 200 degrees C, and what's going to happen is that we're going to migrate the allyl group from the ortho to the from the oxygen to the ortho position. Okay, so we're going to take the whole group here, and it's going to migrate to the carbon that's ortho to oxygen. Okay. The mechanism here just involves a paracyclic reaction. Notice how we're just moving 3 arrows like we did in the Diels-Alder reaction. Okay, since the 2 compounds are already bonded, we don't actually make a new ring. We just move the allyl group. Okay, and what happens here is that you make this compound, which is a ketone, and this type of ketone would rather be an enol because an enol is aromatic, whereas this is not aromatic. Okay, so normally enols are the less stable, or not as stable as ketones, but this is a case where the equilibrium is going the other way to achieve aromaticity. Okay, this is a symmetrical allyl group. What if it's unsymmetrical? Well, notice how, just follow these arrows here. If there had been a methyl here, like we have here, there'd be a methyl here, okay, in your product. And so if you do the Claisen rearrangement on this compound, what you're going to find is that the methyl group is going to also be directly attached to the ortho position. So let's just write that one out here for the sake of clarity. Okay, so I'm going to draw it in a different conformation. I'm going to go ahead and draw the hydrogen here. Okay, so we're going to do the Claisen rearrangement. We're going to make the unstable ketone form. Okay. And then this is going to turn into an enol, and that gives us the product. Okay? All right, so let's move the methyl here. If we had actually thermalized this compound, or heat it to 150 degrees, we'd find that the methyl would end up in the end of our chain there, according to this mechanism. Okay, so let's complete each reaction equation here. All right, so this is a 3-step process making this. As you can probably tell, this last step here is the Claisen rearrangement. Okay, so what do we need to accomplish that? Okay, so what we're really needing here is the halide that's going to make the ether that's going to be heated to 150 degrees. Okay, so we'll need this halide, shown in blue here, the SN2 reaction, sodium hydroxide, and this halide is going to give this allylic phenyl ether here, and the thermolysis of this is going to give us the compound that you see here. Okay, here we're looking at what starting material is required to convert or required to make this alcohol right here. Okay, so it looks like we're doing this reagent here you've seen turns nitro groups into NH2 groups. This reagent turns NH2 groups into diazonium salts, and this is a way to turn a diazonium salt into a phenol. Okay, so the original compound we need here is a nitro compound, the nitro compound that corresponds to that alcohol right there. Okay, this is not a benzene ring, this is a thiophene ring, but remember, thiophene rings are also aromatic and can substitute for benzene rings in these processes. All right, here we're going to treat this with nitric acid, sulfuric acid, then KOH and acidify. Okay, so our first process there is an example of electrophilic aromatic substitution. All right, so chlorine is an ortho-para directing group, so chlorine is sending our substituent here or here. Okay. All right, and so what's going to happen here? Well, it's actually going to go here. Remember, naphthalenes, we substitute typically the one position of a naphthalene ring. Okay, we talked about that in the electrophilic aromatic substitution because we can write more resonance forms that don't alter the aromaticity in this ring. And after step one, we're going to make this compound. And in step two, since the nitro group is ortho to chlorine, we're going to, in the next reaction, turn the chlorine into the hydroxy group. And the last one is just the Claisen rearrangement. We're not going to go to this position because this is already substituted. We'll just say that this position is blocked. So we're going to see it go to the other ortho position. And the product that we get there should have the 8-membered ring at the other ortho position, and the bond is going to really be between that carbon and the ortho position, and this is producing this product right here. Okay, electrophilic aromatic substitution. Remember that OH is a strongly electron withdrawing group and an ortho-para director. It's such a good electron donating group that when you react it with bromine, you do not need any of this FeBr3, so Br2 all by itself will substitute the ortho-para positions. It's kind of hard to stop this reaction at 1. Okay, so this is a real problem with this process because the bromine doesn't really deactivate very strongly, so yeah, it would be hard to stop this at just 1. Okay, if you do the electrophilic aromatic substitution with something that adds an electron withdrawing group to the ring, you don't have any problem because each time you add something, you deactivate the ring, so you don't have to worry about adding more than one of these acetyl groups when you do the Friedel-Crafts alkylation. So here we're going to see mostly para, but some ortho. Okay, and it's easy to stop at 1 since each acetyl group is strongly deactivating the system. The other reactions that would show this feature are, I guess, nitration and sulfonation. Nitro groups and sulfonate groups are really strong deactivating groups. Okay, recognize that the acid chloride, if we had had some pyridine here and no aluminum chloride, we would have added it to the alcohol. But even if you accidentally did that, you could take this phenyl ester here and treat it with aluminum chloride, and you get something called the freeze rearrangement, which gives you the acetyl group in the ortho-para position. It's as if you were basically doing the electrophilic aromatic substitution of phenol itself. Okay, and the reason for this is because the electrophilic aromatic stable substitution products are more stable than the esters. There's a really nice resonance interaction that we can write here. Okay, so let me just write that. Okay, so what we see here is that the electron withdrawing group and the electron donating group are kind of we call this type of interaction a push-pull interaction, but the electron donating group is satisfying the needs of the electron withdrawing group, and this is a very favorable situation. Okay, another reaction that's like electrophilic aromatic substitution is called the Kolbe-Schmidt reaction, except it's done under basic conditions. All right, so here we're going to take sodium hydroxide and then CO2 at high pressure, and we're going to put the carboxylate group into the ortho position, and if you acidify this, you get the orthohydroxy phenyl or orthohydroxybenzoic acid derivative. All right, the reason this works is because if you look at the phenol anion and what I've shown here in magenta, you can sort of see what we call an embedded enolate. This is an enolate. And recall that enolates will react with CO2. Okay, and gives you this compound initially. The keto-enol tautomerism is going to favor the enol because it's aromatic. We still have an acidic proton, so under basic conditions, you're going to get this dianion, and acidification gives you this compound here. All right. Phenols also undergo kind of a rather unique oxidation reaction. Their oxidation products are these types of products called benzoquinones, okay? All right, so it's easiest to do this on compounds where the two OH groups are para to each other. Okay, it can also be done without the second OH group, but it requires harsher reagents. But many of the oxidants we've seen in the past, like the chromate oxidation or the silver oxidation in the Tollens reaction, will turn the hydroquinone into the benzoquinone. And it's easy to turn the benzoquinone back into a hydroquinone with various reducing agents, sodium borohydride being a commonly used one. Okay, we're going to end this chapter with a synthesis problem followed by just a kind of a practical application we're going to see for quinones. Okay, so let me just say that this redox reaction you see at the bottom is very important in biology. It's how a lot of biochemical systems store or release electrons, is through the interconversion of the hydroquinone and the benzoquinone forms of these types of systems. Okay, so we're going to divide a method to accomplish the following reaction, and there should be no ortho-meta-para ambiguity in your synthesis. This is telling us that we're probably going to have to use the Claisen rearrangement, because the Claisen rearrangement is the only reaction where we can direct specifically ortho and not ortho-para. Okay? All right. The only good method we've had is to or of all the methods, we seem to prefer the one where we're using the diazonium chemistry. So we're going to invest several of the steps here in transforming the benzene ring into an OH group. Okay, so in that transformation of a benzene ring to a phenol, some of the intermediates have electron withdrawing groups. That would be the nitro intermediate, and some of the intermediates have electron donating groups. That would be the amine intermediate. So we have to introduce groups strategically when we have the right group in place. All right, so here's our synthesis. It's kind of long, okay? Recognize that we're inevitably the last step of this reaction is going to be to turn a phenol into a methoxy group, okay? All right, so the Claisen rearrangement is not going to give us a propyl group, it's going to give us an allyl group, okay? This is a propyl, N-propyl more specifically, and this is an allyl group. Only an allyl group can be installed by the Claisen rearrangement, but of course we can just take our alkene and hydrogenate it, okay? All right, so this is the precursor that we need. Okay, because for steric reasons, we're probably going to see the Claisen rearrangement not go there, but go to that ortho position. Okay, we're going to make this compound from the corresponding phenol by doing the Williamson ether synthesis. Okay, bromine is meta to the hydroxy group, so it needs to be there before the hydroxy group's attached, right? Because all of these OH, O-allyl, OH, OMe, all of these direct any new substituent to the ortho-para position, and this is meta. So we're going to have to introduce this bromine when we have the right combination of groups on our benzene ring. All right, the immediate precursor to a phenol is the diazonium salt, okay, which is made from the aniline derivative, which is made from the nitro compound. And right here you see this is our only intermediate in this sequence here that has a really good EWG. This is also a good EWG, but it's so reactive you can't use it that way. So we're going to introduce our bromine right after our nitro group, and this reaction from the electrophilic aromatic substitution chapter, chapter 12, will nicely turn our benzene into nitrobenzene. Okay, so this is kind of a long synthesis problem, but 4 of the steps are in really just a standard transformation of a benzene ring to a phenol through the diazonium chemistry. Okay, so this will be the last one we look at. Last slide here. Just want to say a few words about phenols. Okay, if you look at a class of compounds used in food supplements or vitamin supplements, a lot of them are touted as being antioxidants. They prevent free radical damage in the system. And what you find here is that a very high percentage of the compounds that are called antioxidants are phenols. One of the most important ones is vitamin E. Okay, so how does vitamin E trap radicals? So here's a reactive radical in our system. It's going to pull this hydrogen off right here. Once this hydrogen is pulled off, we can now transform this into a hydroquinone, and this is a reversible reaction. We also have lots of resonance structures we can write for that radical. Okay, we'll just call that group R, sorry. Okay, and that radical right there is tertiary, so that's pretty good. And we can write some more allylic type resonance forms. The gist here is that the radical that you get from pulling that hydrogen off is much more stable and hence less reactive than the unstabilized radical that you started with. So it's going to do less damage to when it's inside of a cell. Okay? All right. And you can actually remove the all radical character altogether by pulling another hydrogen off. In this case, going to pull a hydrogen off to make a double bond, and now all radicals have been removed from the system. Okay, in cases where you have stable enols, you see a lot of similar properties of phenols, and another compound that's similar in this vein is vitamin C. Okay, it's also an antioxidant. This tends to be, vitamin E is fat soluble. And this is water soluble. Okay. All right, so you can pull a proton off here and pull another proton off and generate this one, and this has also removed the radicals from the system. Okay, so antioxidants are important compounds for preventing free radical damage, and the idea here is that when you pull hydrogens off, you get relatively stable radicals, and you can even remove all radicals altogether by doing a second hydrogen abstraction reaction. So they're very important in biology. Okay, so this is where we're going to end the phenol chapter. Okay. All right.